title today is Chemical Equilibrium. Chemical equilibrium. All right, and we're going to start by looking at this reaction here. So we've got a couple of nitrogen dioxides. Okay, and nitrogen dioxide is a dark brown gas. And those two nitrogen dioxides are going to collide together to form dinitrogen tetroxide, which is a colorless gas. All right, so what you would expect then is that as long as this reaction goes all the way to completion, right, that we are going to have the dark brown color disappearing, and eventually what we're going to have in our closed container, right? So this is in a closed container, not open where everything can escape. And what we should find then is that we've got a colorless gas in there after a certain period of time. Well, over time, that's what happens. The reaction goes to colorless, but then it goes back to being light brown. So let's write that down. Over time, this reaction goes to colorless. But then back to light brown. And so what does that tell us? Okay, what has to be occurring for this to happen? Well, we must be having the reverse reaction occurring as well, right? The dinitrogen tetroxide must be decomposing back into NO2. So in reality, for this reaction in a closed container, this no longer is sufficient. We have the double-sided arrow. Okay. And so we're introduced to this thing called chemical equilibrium. Most reactions are reversible. Not all reactions, but most reactions are reversible. Okay, and if they are in a closed container where none of the product can escape, or they are in aqueous solution where none of the product can escape, then most reactions actually do begin to reverse themselves at some point. Okay, now we say that, okay, so when this thing goes to light brown, then it stays this same shade of light brown, meaning that we've reached some sort of equilibrium. Okay, so let's write this down. Chemical equilibrium is the condition. Chemical equilibrium is the condition where the concentrations constant. That's fine. Okay, so we say that equilibrium, when a chemical reaction reaches equilibrium, what that means then is that it's reached a point where the concentration of reactants and the overall concentration of products are not changing. So what that means then is that the forward reaction rate is equal to the reverse reaction rate. So at equilibrium, the forward and reverse reaction rates are the same. Okay, so concentrations of reactants and products remain constant, and the forward and reverse rates are equal. Okay, so this is important because you guys, nothing has stopped. Reactants are still colliding, forming products, but at exactly the same rate, products are decomposing back to reactants. Okay, so at equilibrium, motion hasn't stopped. There's still all kinds of activity going on. Reactants are becoming products, and products are going back to reactants at the same rate. So their overall concentrations are staying the same, but there's all kinds of frantic activity that's still occurring. Okay, that's just our first little introduction to equilibrium. We're going to be talking about equilibrium for weeks. And it is one of those subjects that the more you understand about it and the more you think about it, the more questions you have about it. And the more confusing it can become. So, we're going to do some really straightforward stuff today. Easy stuff today. But as we go on, things are going to get more and more confusing. But I have faith in you. Okay, we're going to be able to get through. Okay, now, if we say, and I'm going to write this down in a minute, if we say that equilibrium lies to the right, that means that once the reaction reaches equilibrium, it's going to favor lots of product. So product will predominate. If we say that equilibrium lies to the left, that means that once the reaction reaches equilibrium, that reactants will predominate. All right, so let's move to the other side like this. If equilibrium is described as being far to the right, this means it favors products. that remain. Equilibrium is reached. And for small. Okay, if equilibrium is described as being far to the left, and I've written on here far to the left, but it doesn't even have to say that, you guys. Equilibrium lies to the left. Equilibrium lies to the left. That means that this means it favors reactants. And this is all just a lot of vernacular. Favors reactants. So what that means is the amount of products that remain when equilibrium is reached small. All right. We're just going to get this down, and we will continue talking about this. Continue talking about this for the next 2 months. Okay, so how is the equilibrium condition expressed? How is the equilibrium condition expressed? Well, we use the law of mass action. The law of mass action is used. So, that would be, for example, JA plus KB gives you LC plus MD. Okay, this is just a model. This is just an example. This is the coefficient for this first reactant A. This is the coefficient for this second reactant B. The coefficient for this first product C. And the coefficient for the second product D. But right, we know that equations, reactions, don't necessarily always follow this model. Okay, so how do we write the equilibrium expression for this? Okay, the equilibrium expression for this is big K is equal to, we put products over reactants, C to the L power times D to the m power over a to the j power times b to the k power. This is an equilibrium expression. Products over reactants raised to the coefficient power. At equilibrium, we've always got this quotient, which we call K, the equilibrium constant. And as long as we are at the same temperature, K, the quotient between the products and the reactants at equilibrium, will always be the same. Depending on how much of it we start with, the concentrations at equilibrium aren't necessarily the same. Because if we start with more reactant in terms of concentration, we'll end up having more or less product, but their ratio at equilibrium will always be the same. Okay, so let's look at a real example here. Let's write a reaction. So not the law of mass action, but let's just do a regular old equation and write the equilibrium expression for it. So let's use, what did I use? 2H2, 2 hydrogens react with an oxygen. Give us 2 waters now. This is a pretty difficult reaction actually to go backwards, to split the waters. This is a pretty difficult one to do. Because the activation energy going backwards is huge. And so it's going to be pretty strange conditions where this will actually occur. But this is just for an example. Just for an example. So in this case, you guys, our equilibrium expression for this is going to be, what is my product? 2 waters, but they're liquid. K equals. When would I put 1? Why didn't I put it? And then we've got hydrogen, and that's squared, and an oxygen. That's to the first, so we're going to move it along. Okay, now I'm going to say this right now, but we'll need to address it over and over again. Why did I leave water out of my expression? Because concentrations of pure liquids and solids don't change. Because they're pure liquids and solids, every change in mass has every change in molarity, every change in moles has the same change in liters because it's a pure substance. So in terms of concentration, pure liquids and solids really don't have a concentration changing, whereas gases and aqueous solutions, changes in volume or changes in moles will change their concentration. So equilibrium expressions only contain gases and aqueous solutions, not liquids or solids. Okay, now, again, K is the equilibrium constant, and it's a ratio between concentrations of reactants to products at equilibrium. Okay, so K is the equilibrium constant. Can tell us all sorts of things. But first of all, a small value of K tells us that equilibrium lies left. Okay, so if we have a small value of K, that tells us that when a reaction reaches equilibrium, it means it's going to favor reactants. What is a small value for K? That means K is less than 1. A large value of K equilibrium lies right. And that is if K is greater than 1. So again, K is the ratio between products and reactants at equilibrium. The only thing that can change the value of K is changing temperature. And why would changing temperature change the value of big K? Well, that's because at equilibrium, the forward and reverse reaction rates are the same. Now, if you change temperature, remember that the forward reaction and the reverse reaction have different activation energies. And so changing the temperature is going to change the forward and reverse rates differently. And so the position of K, how much product we have compared to reactant at equilibrium, is going to change because the forward and reverse reaction rates have different activation energies. So changes in temperature are going to differentially change the rates, if that makes sense at all. Okay, but as long as we're at the same temperature, our ratio will always hold true. Okay, so there's all kinds of things that we can do with that. But what you're going to do tomorrow in class is simply write equilibrium expressions for reactions. And so what we want to do right now is, real quickly on the overhead, again, write the rules for writing an equilibrium expression. Okay, well, that's it. The end of my projector. Last but not least, when writing equilibrium expressions, no, don't come in. unbalanced equations. Products are on top. Reactants on the bottom. All concentrations are raised to the coefficient power and reactants and products, reactants and products that are pure liquids or solids